Hello everyone! As GT Rover team from Gebze Technical University, we are entering our fourth year with a dynamic team of 45 people from different departments. This year's rover has been further developed compared to last year's version. We are excited to introduce FEZA, the fourth rover of our journey.
The equipment servicing task involves performing various tests such as making different equipment and systems operational, performing maintenance on the rover, transferring and storing scientific samples to the lander through different mechanisms. Sequential tests start with the identification of a target and the displacement of the robotic arm. In the next stage, the angles of the 6 axes of the robotic arm are calculated using an inverse kinematic solver to perform the operation on the target. RoboClaw motor drivers adjust the speeds of the DC motors of different powers on the axis using these calculated angles to ensure the robotic arm moves correctly. The motion transmission between the axes is provided by worm gear, differential wrist mechanism and belt drive. In addition, R&D activities are carried out on harmonic gear systems in order to increase and facilitate the precision of robotic arm movement. Incremental encoders are used to provide precise feedback of the movement of the axis and motors.
The extreme delivery mission requires travelers to assist astronauts by completing tasks in difficult conditions. The rover assists the astronaut with tasks such as finding, collecting, and delivering objects. The wheel assembly consists of 3 main components, all produced with fused deposition modeling technology. Airless tiles made of TPU material, the rim, and the motor housing, which contains a motor and gearbox. TPU tiles absorb shocks from fails and impact, preventing damage to electronic components, eliminating the risk of explosion and ensuring efficient driving in different ground conditions. A high reduction ratio gearbox added to DC motor helps the rover climb steeper terrain in challenging competition tests. The rocker suspension system and airless wheels make the rover robust and able to cope with the obstacles. The connection between the 4-wheel drive system and the chassis is formed with aluminum fittings. Versatile antennas on the rover and ground station enable long-distance communication for autonomous and manual driving. The custom drive package allows drive of the rover with speed data compared to encoder data to drive the DC motor.
Powered by Nav2 by ROS2 and advanced sensors such as GPS, encoders and cameras, the rover autonomously navigates, pinpointing its location and avoiding obstacle for efficient, independent mission completion. The Z2 stereo camera are used to create 2D global map and detect obstacles. Employing the A-Search algorithm, the rover dynamically identifies the optimal path to the destination. The rover's position is accurately determined through the utilization of the differential global position system and Z2 camera. The GPS is a highly precise satellite-based navigation system that provides real-time position data. Additionally, Z2 camera is equipped with a magnetometer, which offers the absolute orientation of the rover relative to the magnetic pole. In our robot autonomous application, Aruka markers were detected with highly precision using Z2 camera and OpenCV. This approach reduced collision rate by 80% compared to traditional methods. Test control and data visualization is managed with our web-based React user interface application. There are customizable layouts according to the mission. The rover's position, waypoints, map, planned route, and sensor data are visualized in real time at the base station.
The science team conducts experiments and design a life detection system using chemical, biological, geological, and atmospheric data. Test the hypothesis of extinction, existence, or non-existence of life. A robotic arm used to collect soil samples and the gripper's claw fingers are sterilized with UV light to prevent contamination. Samples are transferred to test tubes that contain a buffer solution and a filter mechanism. This system aims to extract biomolecules from the soil. After filtration, a peristaltic pump moves liquid phase samples to a Raman spectrometer for the detection of biomolecules and to a biosensor for the detection of ATP. Cameras and microscope are used to examine rocks, stones, and fossils to compare data with soil, rock color, and fossil record, revealing past characteristics and age. Integrated sensors in the rover monitor environmental conditions, atmospheric constituents, and soil analysis accuracy to assess suitability for life. The results and data of all analyses are transferred to the interface for interpretation.